In this review video, we'll work through a set of real exam-style Calculus 1 problems on applications of integration. These are the same types of problems I used to give my university students to review for their exams, and the examples come directly from my Calculus 1 course videos, just the problem-solving portion without the lecture, so you can stay focused on the examples. You can also download the free PDF of all the practice problems on my website, understandthemath.com. Let's get started. In this example, we're going to find the area of the region enclosed by the following curves. Our first curve is y is equal to x plus 2, and the second curve is y is equal to minus x squared plus 4. The first thing that we want to do is to find the points where the two curves intersect. We're going to do this by setting the two curves equal to each other. So we have x plus 2 is equal to minus x squared plus 4, and we need to solve for x. Let's pull everything over to the left, and that gives us x squared plus x plus 2 minus 4 is equal to 0. So we have x squared plus x minus 2 is equal to 0. We can factor this as x plus 2 and x minus 1. And this gives us that x is equal to minus 2 and x is equal to 1. Now what we need to do is find the y value of these points of intersection. To do this, we are going to look at the two curves that were given and use the easier one. That's going to be this one, y is equal to x plus 2. So let's write that up here. Y is equal to x plus 2. When we have x is equal to minus 2, y then is equal to 0, and we get the point minus 2, 0. And then when x is equal to 1, y is equal to 3, and we get the point 1, 3. Let's go ahead and highlight these because we are going to need to plot those in our next step. Our second step is to graph the region. We're going to begin by plotting the two intersection points that we just found. The first point is at minus 2, 0, so we'll put that right there. And then the next point is 1, 3, and we'll put that point right here. I find that I like to wait to label these 2 points until I go ahead and get the graphs drawn. That's what we're going to do now. We are going to graph our two curves. Let me put them up here so we remember what they are. We have y is equal to x plus 2, and we have y is equal to minus x squared plus 4. Let's graph the line first. That is just going to go between our 2 points of intersection. And then our second curve right here is a parabola that opens downward, and the vertex is 0, 4. Our vertex is right here, and we know that it's going to go through our two intersection points, so we can just graph it like this. There we go. The area that we're going to find is this area in here. Let's go ahead and let's put some labels on our graph. We'll label our intersection points. This point down here is minus 2, 0, and this point up here is the point 1, 3. Our line is the graph y is equal to x plus 2, and our parabola is y is equal to minus x squared plus 4. It really helps to label the graphs when we go to set up our integral. The next thing that we're going to do is choose the formula for our area. We need to choose the formula based on if we want to integrate with respect to x or respect to y. If we integrate with respect to x, we want one curve on the top and one curve on the bottom. If we draw some straight lines, you can see from our graph that we do have one curve on the top and one curve on the bottom. Now let's see if we can integrate with respect to y. We need to see if we have one curve on the right and one curve on the left. If we draw a horizontal line, you can see that we have the same curve on the right that we do on the left. So we do not want to integrate with respect to y. So we are going to choose the formula. Our area is the integral from a to b, the curve on the top, yt, minus the curve on the bottom, y sub b, dx. Our curve on the top is our parabola, and our curve on the bottom is our straight line. Let's now set up and evaluate our integral. Our area is the integral from x is equal to minus 2 to x is equal to 1. Our curve on the top, which is minus x squared plus 4, minus our curve on the bottom, which is x plus 2. And then we have our dx. Let's now simplify our integral. Minus 2 to 1. We have minus x squared plus 4. And then we're going to be subtracting both x and 2. I think that's the biggest mistake I see students make, is to not carry that minus sign through to both terms. This gives us a minus x minus 2 dx. And this gives us the integral from minus 2 to 1 of minus x squared minus x plus 2 dx. Now we can go ahead and integrate this. Our first term is minus x cubed over 3, and then we have a minus x squared over 2, and then our last term is plus 2x, and we're evaluating this from minus 2 to 1. Now let's plug in that x is equal to 1. This gives us minus 1/3 minus 1/2 plus 2. And then we're going to subtract off minus a minus 2 cubed over 3. We have a lot of negatives there. Minus a minus 2 squared over 2 plus 2 times minus 2. Now let's go ahead and let's simplify this. This is minus 1/3 minus 1/2 plus 2 minus, we have minus 2 cubed, which is minus 8, multiplied by a minus 1. So this is 8 over 3. And then we have a minus 4 over 2, and then a minus 4. This gives us minus 1/3 minus 1/2 plus 2 minus 8/3 plus 4 over 2, which is 2, and then plus 4. This is 2 plus 2 plus 4. That gives us an 8. And then we have a minus 1/3 and a minus 8/3. That's minus 9/3, which is minus 3. And then we have minus 1/2. So this is 5 minus 1/2, and that gives us a value of 9/2. So the area between these two curves is equal to 9/2 or 4.5. In this example, we're going to find the area of the region enclosed by the following curves. X is equal to y squared, and x is equal to y plus 2. The first thing that we want to do is to find the points where these two curves intersect. To do this, we're going to set the two curves equal to each other. So we have y squared is equal to y plus 2. Let's pull everything to the left, and we get y squared minus y minus 2 is equal to 0. We can factor this as y minus 2 times y plus 1 is equal to 0. And this gives us that y is equal to minus 1 and y is equal to 2. Now we need to find the x values for these points of intersection. To do that, we're going to use the easiest curve, and that's x is equal to y plus 2. So So let's write down x is equal to y plus 2. And then when y is equal to minus 1, we get that x is equal to 1. And this gives us the point 1 minus 1. And then when y is equal to 2, we get x is equal to 4. And this gives us the point 4, 2. Let's go ahead and let's highlight these because we are going to need them in our next step. In step 2, we are going to graph the region. We are going to start by plotting these intersection points that we just found. The first point is 1 minus 1, and let's put that point right here. And then our next point is 4, 2. Let's march out 4, 1, 2, 3, 4, and up 2. We're going to hold off on labeling these points until we go ahead and graph our curves. That's what we're going to do now. Our curves are x is equal to y squared, and then x is equal to y plus 2. Let's graph the straight line first. It's just going to go between these two intersection points. Let's now graph this parabola. It is a parabola that opens to the right and has a vertex at 0, 0. So we can just go ahead and let's graph this. And we can see that these two curves enclose this area right here. Now let's go ahead and let's label everything. Our first point of intersection is down here at the bottom, and it is 1 minus 1. And then our point of intersection at the top is the point 4, 2. Let's now label our graphs. Our line is the graph x is equal to y plus 2. And then our parabola is x is equal to y squared. It really helps to put the labels on the graph for when we set up the integral. Our third step is to choose a formula for integration, and we need to decide if we want to integrate with respect to x or with respect to y. If we integrate with respect to x, we're going to have one curve on the top and one curve on the bottom. If we draw some horizontal lines here, you can see if we look at the first horizontal line that there is the same curve on the top and on the bottom. So that tells us we don't want to integrate with respect to x. Let's now see if we have one curve on the right and one curve on the left. If we draw some horizontal lines, you can see that we have one curve on the right and one curve on the left. So we want to integrate with respect to y. Let's write down our area formula. Our area is going to be the integral from c to d of our curve on the right, xr, minus our curve on the left, x sub l, times dy. Our curve on the right is our line, and our curve on the left is our parabola. Now let's go ahead and set up our integral and evaluate it. Our area is the integral from the y value of our intersection point, which is -1 to 2. Our curve on the right, which is y plus 2, minus our curve on the left, which is y squared. And we have dy. Let's go ahead and let's simplify this. This is the integral from -1 to 2 of y plus 2 minus y squared, dy. Now we can go ahead and integrate. We have y squared over 2 plus 2y minus y cubed over 3, and we're evaluating that from -1 to 2. We're going to substitute y is equal to 2 first because that's our upper limit. So we have 2 squared over 2 plus 2 times 2 minus 2 cubed over 3 minus y evaluated at -1. So we have minus 1 squared over 2 plus 2 times minus 1 minus minus 1 cubed over 3. Now let's see what this gives us. We have 4 divided by 2, so that's 2. And then we have 2 times 2 is 4. And then we have minus 8 over 3. And then for this next one, let's simplify what's in the parenthesis first. This is 1/2 minus 2 minus a negative 1 gives us a plus 1/3. This is equal to 6 minus 8 over 3 minus 1/2 plus 2 minus 1/3. 6 and 2 is equal to 8. So we have 8. And then we have minus 8/3 minus 1/3. That is minus 9 over 3, which is minus 3. And then minus 1/2. So this is 5 minus 1/2, which is equal to 9 over 2. Our area then between our two curves is equal to 9 over 2, or 4.5. We're going to walk through 2 examples where we revolve a region about the x-axis. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the x-axis. Let's look at our first example. The first thing that you want to do with these types of problems is to graph each of the curves that you're given. Just to save time, I've already done that. We have the curve y is equal to the square root of x minus 1, and then we have 3 lines. X is 2, x is 5, and y is 0. The region that we're going to be revolving is the region that's bounded by this curve and lines. That's this region right here. The radius of our solid of revolution is this radius right here, and you can see that it's equal to y. So the formula that we're going to use is the volume is equal to pi times the integral from a to b y squared dx. And that's because our cross-sectional area is pi r squared. X is going to range from 2 to 5, and this is our y. Let's go ahead and let's put that in. Our volume is going to be pi times the integral from 2 to 5 of y, which is the square root of x minus 1 squared times dx. This is equal to pi times the integral from 2 to 5 of x minus 1 dx. This is equal to pi times the integral of x, which is x squared over 2, minus the integral of 1, which is x, and we're going to evaluate this from 2 to 5. This is equal to 25 over 2 minus 5 minus the quantity 2 squared, which is 4 divided by 2 minus 2. I always write it like this so I don't forget to take that negative and multiply it through to both terms. Let's see what this gives us. This is equal to pi. We have 25 over 2 minus 5 minus 2 plus 2, so that's just minus 5. We'll get a common denominator of 2, so this is pi times 25 minus 10 all over 2, and this gives us an answer of 15 pi over 2. The volume of our solid of revolution is then 15 pi over 2. Let's look at our second example. In this example, we have 2 curves. Y is equal to x squared, and then x is equal to y squared. We want to begin by finding the points where these two curves intersect, and we want to find the x value because we're revolving about the x-axis, and we're going to use x for our limits of integration. So I'm just going to write down that we're going to find the x intersection points. To do this, we're going to start with our first curve, y is equal to x squared, and then in our second curve, we're going to solve for y, and we get y is equal to the square root of x. So down here, we're going to let x squared equal the square root of x, and we need to solve this equation for x. The best way to do this is to square both sides. So this gives us x to the fourth is equal to x, and that equation we can easily solve. I'm going to subtract x from both sides, and we get x to the fourth minus x is equal to 0. We can factor this, we'll pull out an x, and we have x cubed minus 1 is equal to 0, and this gives us that x is equal to 0, and x is equal to 1. Now we can go back up to our graph, and we can see that our two intersection points are 0, 0, and 1, 1. We'll go ahead and label that. Because we have a gap between the region that we're integrating, let me go ahead and let's highlight this in green so you can see that region. We're going to have an outer radius and an inner radius. This is our outer radius, and it is equal to y, and it touches our top curve right here. So y is equal to the square root of x. And then this is our inner radius, and it touches our bottom curve. So that height is equal to y, which is x squared. The formula that we're going to use is the volume is equal to pi times the integral from a to b. We have our outer radius, which is y out squared, minus our inner radius, yn squared dx. This is equal to pi times the integral from 0 to 1. Our outer radius we found was root x, so we have the square root of x squared. You have to remember to square it, minus the inner radius, which was x squared, and we square that one as well. And then we have our dx. Before we integrate, let's simplify this integral. This is pi times the integral from 0 to 1. Square root of x squared is just x, and then we have minus x to the fourth dx. This is equal to pi times x squared over 2 minus x to the fifth over 5, and we're integrating from 0 to 1. It's always nice when we have 0 as a limit of integration because we don't have to do as much work. This is then pi times 1/2 minus 1/5. We'll get a common denominator of 10. So this is 5 minus 2 over 10. And we get an answer of 3 pi over 10. This tells us that the volume of our solid of revolution is equal to 3 pi over 10. We are going to look at two examples where we are going to revolve a region about the y-axis, and we're going to use disks and washers. We're going to find the volume of the solid obtained by rotating the region bounded by the given curves about the y-axis. In our first example, we are given a curve, two lines, and a region. I went ahead and graphed these, and you can see that the region that's enclosed by all of these curves is this region right here. When we revolve this region about the y-axis, the first thing that we need to do is find the radius. that radius is this length right here, and our radius is just equal to x. Our volume is pi times the integral from c to d of r squared, which is x squared times dy. We have a dy because we're revolving about the y-axis, and the width of each circular disk is equal to dy. Our volume is then pi times the integral from c to d. C is equal to 0 and d is equal to 4. So we have 0 to 4. Our x squared is equal to y. Let me highlight that. That's right up here. So we just have y dy. This gives us pi times y squared over 2 from 0 to 4. This is pi times 16 divided by 2 minus 0, and we get an answer of 8 times pi. This example that we just did is an example where our region was lying right against the y-axis. In our second example, we have a region where there is a gap between our region and the y-axis. We have two curves, x is equal to y squared, and x is equal to 2y. The region that is enclosed between these two curves is this region right here. And we're going to revolve this region about the y-axis. Because we're revolving a region about the y-axis, we are going to integrate with respect to y, and we'll want to begin by finding our intersection points, and we want the y value for those points. We're going to find that by setting our two curves that we're given equal to each other. This gives us y squared is equal to 2y. Let's pull the 2y to the left, and we can factor out a y. And this gives us that y is equal to 0 and y is equal to 2. Let's highlight that because we'll need that in a minute. Because there is a gap between our region and our axis of rotation, we are going to have an outer radius and an inner radius. Our outer radius right here is given as x is equal to 2y, and then our inner radius right here is given as x is equal to y squared. Let's now write down our formula. Our formula is v is equal to pi times the integral from c to d, our outer radius squared, which is x out squared, minus our inner radius squared, x in squared, times dy. Let's go up here and let's label this as x out, and we'll label this one as x sub n. Now let's go ahead and put this into our integral. This is pi, the integral from 0 to 2. Our outer radius, which is the quantity 2y squared, minus our inner radius, which is y squared squared. And we have dy. Let's simplify this before we integrate it. We have the integral from 0 to 2. This is 4y squared minus y to the 4th times dy. This now, if we integrate it, is 4y cubed over 3 minus y to the 5th over 5 from 0 to 2. This gives us pi times 4/3. 2 cubed is 8, so we multiply that by 8, and then minus 2 to the 5th. That is 32, and we divide that by 5, and then we subtract off 0. To make this easier, let's pull out the 32, so we have 32 pi, and then we have 1/3 minus 1/5. If we get a common denominator of 15, this is going to be 5 minus 3 over 15. So 32 times 2 is 64, and this gives us 64 pi divided by 15. And there's our volume. We're going to walk through an example where we find the volume of a solid of revolution that's obtained by rotating the region bounded by the given curves about the y-axis. In this problem, we are going to be using cylindrical shells. The curve that we're given is y is equal to 2x squared minus x cubed, and y is equal to 0. Just to make this easier, I went ahead and graphed both of these curves. And you can see the region enclosed by these curves in green. You may have previously studied disks and washers, and what sets this problem apart is you can't use disks and washers because in this region, the curve on the left is the same as the curve on the right. So cylindrical shells are the best to use. We're going to be revolving this curve about the y-axis, and the cross-sectional area is cylindrical shells. The thickness of each shell is dx, so we are going to be integrating with respect to x, which means the first thing that we need to do is find the x value for the points of intersection. To do that, we just have to set the curves equal to each other. So we're going to say 2x squared minus x cubed is equal to 0. We can factor out an x squared, and that leaves us with 2 minus x is equal to 0. And we can see then that x is equal to 0 and x is equal to 2. Let's mark these on our graph. Here we have x is equal to 0, and here we have x is equal to 2. So those are going to be our limits of integration. Now what we have to do is look up here at our formula. Our formula for the volume of the solid that we're going to get is 2 pi times the integral from a to b, that will be from 0 to 2, r times h dx. What we need to do now is find r and h. This is our radius, and this is our height. The radius is the distance from the curve to the y-axis, and that is equal to x. And then h is the distance from the x-axis to the curve, and that is equal to y. Now we can go ahead and write down our formula. Our volume is 2 pi, the integral from a to b, r times h dx. So this is 2 pi, our a is 0, and our b is 2. Our radius is x, our height is y, and we're integrating with respect to x. We now need to substitute in that y is our curve 2x squared minus x cubed. This gives us our volume is 2 pi times the integral from 0 to 2. We have x, and then we have 2x squared minus x cubed dx. Before we integrate this, let's simplify what we're going to be integrating. This is 2x cubed minus x to the fourth times dx. Now we can go ahead and integrate this. The integral of 2x cubed is 2x to the fourth over 4. And then we subtract off x to the fifth over 5. And we're integrating this from x is 0 to x is equal to 2. Now let's substitute in that x is equal to 2. So we have 2 times 2 to the fourth all over 4 minus 2 to the fifth over 5, and then we subtract off 0. This gives us 2 pi. 2 to the fifth is 32. So we have 32 over 4 minus 32 over 5. Let's pull the 32 out. So this gives us 64 pi, and then we have 1/4 minus 1/5. We will get a common denominator of 20. And then we get 5 minus 4 on top. So this is 64 pi over 20. And each number is divisible by 4. So this gives us an answer of 16 pi over 5. Our volume then is equal to 16 pi over 5. Let's now walk through an example where we are going to find the volume of a solid obtained by revolving a region about the x-axis, and we're going to use cylindrical shells. The curves that we're given is x is equal to 1 plus y squared, x is 0, y is 1, and y is 2. The first thing that you want to do when you're solving this type of problem is to graph these curves. I've already done that to make things easier. Here's the curve. X is equal to 1 plus y squared. Here's the line y is 2. Here's the line x is 0. And here's the line y is equal to 1. So the region that we're going to be revolving is the region that is enclosed by that curve and those 3 lines. We're going to be rotating this region about the x-axis, and we're going to use cylindrical shells. And here's the formula that we are going to be using. What we need to do first is find the limits of integration. We are integrating with respect to y because the thickness of each of our cylindrical shells is equal to dy. The first thing that we need to do is to find the points of intersection of all of these curves. And because we're integrating with respect to y, we need to find the y value. Because 2 of our curves are lines, we actually don't have to do anything. And we can see that we're going to integrate from y is equal to 1 to y is equal to 2. So let's just mark over here, c is equal to 1 and d is equal to 2. Now what we need to do is find r and h. Our radius is right here. I'm marking this in blue. And it is the distance from the curve to our axis of rotation, which is the x-axis. So this is just equal to y. And then the height, which I'm going to mark here in red so that you can see it. And that distance, we'll mark this up here, is h is equal to x. Now we can go ahead and write down our formula. I'm going to write the general formula first. This is 2 pi, the integral from c to d of r h dy. Now we can substitute in what c and d are. C is 1, d is 2. Our radius, let me highlight this so you can see it, is equal to y. And then our height is equal to x. And we're integrating with respect to y. Now what we have to do is substitute in what x is. X is given by our curve 1 plus y squared. And let's go ahead and put that in. We get 2 pi, the integral from 1 to 2, y times 1 plus y squared dy. Before we integrate, let's go ahead and multiply this out. We have 2 pi times the integral from 1 to 2. Inside, we have y plus y cubed times dy. Now we can go ahead and integrate. This is 2 pi. We have y squared over 2 plus y to the 4th over 4. And we're evaluating this from y is 1 to y is 2. Let's first put in that y is 2. 2 squared is 4, so we have 4 over 2. 2 to the 4th is 16, so we have a 16 over 4. And then we subtract off 1/2 and 1/4. Let's combine our fractions. We have 4 halves minus 1 half, so that's 3 halves. And then 16 over 4 minus 1 over 4 is 15 over 4. Looks like we can get a common denominator of 4. So this is 6 plus 15. We can cancel the 2 into the 4. So this gives us 21 pi divided by 2. And this tells us that our volume of revolution is equal to 21 pi over 2. Let's now look at our third example. In this example, we have a force of 8 pounds, and this force is required to hold a spring stretched 2 inches beyond its natural length. We want to find how much work is done in stretching the spring from its natural length to 8 inches beyond its natural length. The force required to hold the spring stretched is given by Hooke's law, and that's F is equal to K times X, where K is equal to our spring constant. Because our force is a function of X, the work is going to be equal to the integral from A to B of our force, which is our f of x, times dx. To evaluate this integral, we need to find A, B, and K. Let's find K first. K can be found by the equation F is equal to K times X. Since a force of 8 pounds is required to hold a spring stretched 2 inches beyond its natural length, we can let our force be equal to 8 pounds. And then we have our K, and then X is going to be 2 inches. K then is equal to 8 pounds, all divided by 2 inches. The standard units for work is foot-pounds, so we need to change our inches to feet. So we're just going to multiply by 12. And we get 8 times 6, which is 48. And our units then are pounds per foot. Now let's find A and B. We need to find the work done in stretching the spring from its natural length to 8 inches beyond its natural length. When the spring is at its natural length, it's not stretched at all, so A is going to be equal to 0, and then B is the length that the spring is stretched, and it is going to be equal to 8 inches. We also need to convert this to feet, so we are going to divide this by 12. 8 divided by 12 is 2/3. So B is 2/3 feet. Now we can go ahead and evaluate our integral. Our work is the integral from 0 to 2/3 of our force F, which is K, which looking back up here is equal to 48. So we have 48 times x dx. This is equal to 48 x squared divided by 2, evaluated from 0 to 2/3. This is 24x squared, again evaluated from 0 to 2/3. If we substitute in that x is 2/3, we get 24 times 2/3 squared, and then we're going to subtract off 0 for our lower limit. This gives us 24 times 4 divided by 9. We can divide 3 into both 9 and 24. So this gives us 32 divided by 3, and now we need units. Our force was in terms of pounds, and our distance is in terms of feet. So our units are foot-pounds. If we want to know what this is in terms of a number, we can say that our work is approximately equal to 10.667 foot-pounds. We're going to find the average value of a given function on a closed interval. Let's look at our first example. Our function is f of x is equal to sine x, and the closed interval is from 0 to pi. Just to make things easier, over here on the right, I have written down the formula for the average value of a function on a closed interval. We're going to start by writing down this formula. Our average value, AV, is 1 all divided by b minus a of the integral from a to b of f of x dx. I think the hardest part of doing these problems is just remembering that formula. Let's go ahead and let's put in what b and a are. B is pi and a is 0. So we have the integral from 0 to pi, and we substitute in that f of x is sine x. And then we can just go ahead and integrate this. This is 1 over pi. The integral of sine x is minus cosine x. And we're going to evaluate this for x is equal to 0 to x is equal to pi. This gives us 1 over pi minus cosine pi minus a negative, so that's plus cosine of 0. You really have to watch your negatives with this problem. Cosine of pi is negative 1, so this is minus a negative 1, which gives us a positive 1, and then cosine of 0 is 1, so we get an answer of 2 divided by pi. This is approximately 0.637. So we have an exact answer and an approximate answer. We can understand our answer better by looking at this graph down here on the right. The blue curve is the function f of x is equal to sine x from x is 0 to x is pi, and the green line is our average value. That's all for this exam review. I hope it helps you as you prepare for your exam.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.